Okay, we're back. Now we're going to talk about antiderivatives and what those bad boys are. So you know what a derivative is, where say I have a function f of x, and I want to take the derivative, which would be f prime x. And boom, and I have a bunch of rules that I can apply, like I got the power rule, I got quotient rule, I've got the other rules that I can remember the name of, and a bunch of stuff that you can use, which we've learned before. But what happens when you want to go back in time? Let's say I'm given f of x, and I'm told find the function that f is a derivative of. So I would be trying to find big fx. I mean, that's a common way to say that's the function above it. Um, but yeah, another way to look at it is like f prime prime x. So if I go up, that's f prime x is the antiderivative of f prime prime x, and f of x is the antiderivative of f prime x, and vice versa. F prime x is the derivative of f of x. And in concept, it's not any more complex than that. It's just the antiderivative, like the opposite of the derivative. Instead of going down, we go up. So, this is useful for a lot of things, which we won't get into right now because it's more complex and that gets into integration, but this is the first step towards learning integrals. Anyways, we have a few rules for calculating this. Uh, Most of it is just intuition, like you already know your other stuff. All you have to do is work in reverse. For example, we have our sine, cosine, tangent, and cosecant, secant, and cotangent. And the derivative of each of these is going to be cosine, negative sine, tangent is going to be secant squared. You're going to be negative cosecant squared. And you are going to be secant times tangent. And you are going to be negative cosecant times cotangent. So when you want the antiderivative, you just have to go back in time. So let's say I'm given cosine. It's like cosine of x is equal to f of x. What, pray tell, is the antiderivative? Wait, can you see that? Okay, you can see it. Yeah. What is the antiderivative of cosine x? Obviously, it's going to be sine of x. So big fx is equal to sine of x, or the antiderivative. Now we can do, I don't know, like secant times tangent, where it goes, hey, f of x equals secant of x times tangent of x. What's the antiderivative of that? I can say, oh, that's just secant x. Easy. Still not too difficult. I got a message.
All good, all good. Don't worry about it. It looks like a test tomorrow.
Respond with this stuff. Awesome. I got the Riz. Anyways, it can get a bit more complex, only slightly, when you can be like, hey, bro, what is the derivative or the antiderivative of sine of x? So, what you can translate this to is going to be negative 1 times negative sine of x. And we know that negative sine x is the derivative of cosine, so we get negative 1 times cosine x, which means that the antiderivative of sine of x is negative cosine x. And we can go back in the other direction to check our work. So what's the derivative of negative cosine x? Well, I know the derivative of cosine x is negative sine x, so negative 1 times negative sine of x is equal to sine of x. That's the trick here. You can actually just, once you have your answer, differentiate again, and like it's like jumping back and forth in time to check your answer. So if you know your derivative rules really well, you will not have a problem with antiderivatives. I would remind you of your the other things, your other trigonometric things, the inverse, no, not inverse trig, inverse trig, yeah, inverse trig, where sine -1, it's not equal to, but turns into 1 over the square root of 1 minus x squared. Cosine -1 turns into -1 over square root of 1 minus x squared. Tangent, -1, turns into 1 over 1 plus x squared. Cotangent turns into -1 over 1 plus x squared. I think it was cosecant. Cosecant turns into -1 over x times the square root of x squared minus 1. And secant, finally, turns into 1 over x square root of x squared minus 1. And yeah, that's how it works. So if I'm ever given something like this, I can just be like, oh, I already know what the antiderivative for that is. So here's an example. Let's say I have 23 over x root minus 1. And the problem is like, hey, what's the antiderivative of f of x, which is this? Well, I can factor out 23 to get 1 over x squared minus 1. And then I know that factors that are constants don't apply to derivatives unless it's like a power rule. So it's going to be 23, and the antiderivative of this, go back up here, it's going to be secant, so 23 secant x. And I can go back in time, 23 times the derivative of secant x, that's the derivative here, and then back upwards, 23 over x times the root of x squared minus 1. Easy. Now, let's introduce the actual rules. Actually, maybe I should probably talk about the constant of integration first. So, I've been lying to you. This isn't actually all there is to antiderivatives. So you know in a derivative when you have, I don't know, let's say 3x squared plus 5x minus 1. When you take the derivative of this, we get 6x plus 5, and then this sad, lonely little 1 is deleted. It gets booted off into the shadow realm, and we never see it again, because we are now in derivative land. So if you wanted to take an antiderivative of something, there is an imaginary number right there that we don't know what it is, because 3x squared plus 5x minus 1 and 3x squared plus 5x plus 622, these both have the same derivative if you do them both. So if we're coming up from the bottom, which one is it? Which one is my true antiderivative? We don't know. So what we do is we add in this c, which is the constant of integration, which says we don't actually know what this constant is, but that it is a number that exists. It could be 0, could be 713, who knows? So whenever you take an antiderivative of anything, after taking the antiderivative, like for example, we got 23 secant x from the last problem, we add c to the end. And we're going to call it c1, because if we go up another antiderivative, we're going to have to do c1x, and then whatever this turns into, plus c2, because we went up another antiderivative, there was another constant on the other one before that. So I hope that makes sense. Whenever you take an antiderivative, you have to add in c, which is our constant of integration. That's what it stands for. And it's just a number that we don't know what it is. You can figure out what that number is if you are given a coordinate where it says, for example, 5x plus 1, and at x equals, and we're given a coordinate at x equals 3, y equals, I don't know, 8. So find the constant of integration for our antiderivative. So we just go back in time. So I'm just gonna do this quick. 5 over 2 x squared plus x, and then we plug in 3 for x. So 5 over 2 times 9 is going to be 45 over 2. Oh yeah, and plus c. Plus 3 equals 8. Oh yeah, and then plus c. I keep forgetting the constant. Plus c equals 8. So 45 over 2 plus 3 is equal to 51 over 2, which is equal to 25.5. So I'm just going to duck down here. 25.5 plus c equals 8. So if I subtract 25.5 from 8 minus, I get c is equal to negative 17.5. Boom. So now I know that my true antiderivative is this equation. 5 over 2 x squared plus x minus 17.5, or 35 over 2. We can just make it simple like that. 35 over 2. Easy. And that is our true antiderivative because we have identified our constant of integration. Okay, so you might have noticed that when I was doing this, when I went back in time from 5x, I got 5 over 2 times x squared. So this is a reversal of the power rule, and there is a small little formula for it that makes it simple, but the concept is that when you go back in time, you have to undivide, or you have to divide by the exponent that you're coming from. So it's going to look like this. And at this moment, I'm going to start talking about different, what are they, formulas to know how to do antiderivatives. So x to the n, the basic power rule is equal to, or not equal to, turns into, when we take the derivative, dx, n times x n minus 1. So what is the reverse of this, you might ask? It turns into x to the n equals x to the n plus 1 divided by n plus 1. Easy. Yep. And so if you have a constant in front of it, it's just going to be the constant times that. Or an even better way to write it would be constant divided by n plus 1 times x n plus 1. So an example could be x to the negative 2/3 and 5. So how do we solve this? Well, if we use the formula, it's going to be x plus 1 is going to be 1 over 3, or n plus 1 is going to be 1 over 3, divided by 1/3 is equal, and then 5 on the front. So 5 divided by 1/3 is technically 5 times 3, so 15 x to the 1/3 plus c is going to be our antiderivative of 5x to the negative 2/3. And we can take the derivative of this. So 1/3 times 15 is going to be equal to 5. And then x to the negative 2/3. And then c we can cross out because it's just a constant, and we get the derivative that we started with. Okay, let's move on to the next rule. I'm going to write this over here. X n plus 1 over n plus 1. Okay, the next one is when you have an inverse. This only applies when you have x to the power of negative 1. Uh, so when you have x to the negative 1, which is just 1 over x, the antiderivative of this, if you remember, is actually ln x. Now it's not x to the negative 2, uh, which would be 1 over x squared. That's not what this is. This is specifically 1 over x. So I can demonstrate this. I was about to demonstrate this, but I already forgot. Oh yeah, let's try and use the power rule on that. So if we have negative 1, we can go x n plus 1, negative 1 plus 1, over negative 1 plus 1. We get x to the 0 over 0. We have a division by 0 error because it's the derivative of a natural log, and it's not valid at those values. And that's where you get a problem. So you have to remember that x to the negative 1's antiderivative is ln x. Okay. Now we have e to the x. So if the derivative of e to the x is e to the x, then the antiderivative of e to the x is going to be e to the x plus c, technically. But specifically when we look at an instance of e to the x, it's going to be exactly what it is. An example of this could be e to the 2x. So in this case, we have to apply the chain rule. What do we have? So all I have to do it is do it normally. So we get e to the 2x, but we have to divide by 2 because that's what's inside our inside the top. Yes. So we end up with 1/2 e to the 2x. And if we do it again, we're going to end up with 1/4 e to the 2x. And if you go back in time, you'll actually notice that if I take the derivative of e to the 2x times 1/2, it's going to be, of course, e to the 2x because that doesn't change. And then the chain rule, the 2 is going to be multiplied by whatever's outside. And if we want to end up back at the beginning with nothing right here, then we have to put 1/2 there. And 2 times 1/2 is 1. So 1, and boom. Easy. So e to the x is still e to the x. Final rule, b to the x, where b is a constant, and x is right there, is going to be b to the x over ln b. And I don't know how to explain it further than that. Maybe there's some examples. Let me check. Okay, spoiler alert, there weren't any examples, so I guess it's not going to be on the test. I really hope not, because I don't think I'll remember that rule. Anyways, it is 6:35. I think I might go get dinner. But that's it for antiderivatives besides examples. So in the next video, we'll practice a bit, and then we will move on. Thanks for watching.